Okay, so let me go through and show you how this works in practice. And in particular, I'll illustrate it by using the radial basis function kernel, because that one is a universal approximator, as I mentioned, for the space of continuous functions. So you could really use that for a very broad range of problems if you didn't have other inductive biases that preferred something else. Okay, so I'm going to start pretty simple, and we'll just kind of keep the function that we're trying to target basic. In this case, it'll be sine of x. So clearly that's a nonlinear function. So using unkernelized linear methods would not do very well on this task. And I'm also going to add a fair amount of noise to it, so there are a fair number of outliers. Okay, so the basic task, of course, is you're given the data yi, which is the target function plus some noise, and your task, of course, is to identify the hypothesis, a fitting function. And here I'm calling the space H linear, but actually I'm thinking about this being a kernelized linear regression. So this actually can fit nonlinear functions in the original input space. So it's going to be linear in the feature space, and that makes all the linear algebra in theory very nice. Okay, so the kernel ridge regression then is to find a minimizer, of course, of the regularized least squares problem. And of course, as I showed you on the previous slide through our derivations, that the final solution can always be written in this form of being a linear combination with these coefficients AI of kernel evaluations centered at each of the data points. And when I want to evaluate it at some unknown new point x, I simply do these kernel evaluations of xix. Okay, so that's really nice. So let's look in the case when I use the radial basis function as our kernels. And so what that's going to be is a Gaussian. It'll just be a little blob, as you can see here. Let's just fix x for a moment. So if I take y at x, I'll get 1. And then as y deviates from x, this decays off. And the rate that it decays will be given by this hyperparameter gamma for the kernel. So basically, the bigger gamma is, the more tightly concentrated the kernel will be around x. Okay, so let's make the choice where we have just 100 samples and gamma is 10. And let me show you what happens when you vary the regularization parameter lambda. And it's really going to be quite crucial that you find a good value for lambda in practice, as you'll see in a minute. So this is now the basic setup. You can see my data points here in black. It's basically the sine curve plus some significant noise, as you see. And then what I'm showing here is just one realization when I had a very small regularization term here for lambda, in particular 10 to the negative 2. And so you can see here, you're already seeing how the RBFs kind of overfit, right? Instead of going nice and smoothly along this little gap, what happened to the RBF? It went right up there and tried to grab that outlier point. And similarly with some of the others here. And this will become especially a big issue when you're doing least squares regression, because it's basically penalizing the square deviation. So the farther an outlier is, and the more influence it's going to have, which is not so great. And we're going to see for certain regression tasks that can be really detrimental, and that'll motivate what we call support vector regression, and what will be, I'll talk a little bit about that. That'll really be helpful when you have kind of unpleasant outliers to deal with. So how does this fit for different choices of lambda? These are some of the things that you need to think about. There are different choices of the gamma width that you'll have to grapple with. That'll typically be done through cross-validation. As we get into some of the more practical methods, I'll talk a little bit about cross-validation in one of the lectures. So hyperparameter choice then becomes really important to get good results in these problems. And that kind of makes sense if you think about it, because the radial basis functions have really, really high capacity if they have small width. In other words, if I take gamma to be a really large number, I can get a really, really rich collection of functions. And as I mentioned a moment ago, they are universal approximators for the space continuous functions. So what's going to happen here is, if I'm not careful, I'm going to way overfit my data. In other words, if lambda is not big enough, I'm going to way overfit my data and essentially fit not only the underlying signal that I was interested in, but also the noise. Okay, so let's see how this plays out now when I change that lambda parameter from 10 to the negative 2, and I'm just going to sweep over a really large range to give you an intuitive feel of the role that the lambda parameter plays. So you can see what I did here is I swept over 10 to the negative 2 all the way up to about 10 to the 4. And okay, so obviously this kind of shows you one of the challenges that's going to come up in a lot of machine learning training settings, which is that you'll have hyperparameters that for some value theoretically will lead to really great performance, but you have to do some work to figure out what that hyperparameter should be. Okay, so you can see what went wrong here is that when it was too small, it fit the noise, and that sort of overfit, and when it was too large, it underfit, right? Of course, what's going to happen is if lambda goes to infinity, it's going to completely ignore the squared error term, and you're just going to get weights that are effectively 0. So that's obviously an issue, and we'll talk about how we're going to address that with cross-validation. That's essentially going to be a technique where I hold some of the data out, and I kind of look at what happens when I fit the data on a new collection of data that I haven't seen before, and I sort of use batches like that, sometimes recycled from the initial data that I started with, in order to see the variability in the fit. And often this can be used to do selection of hyperparameters by balancing fitting data well against reducing the variability. Okay, so what happens if I kind of do this grid search is I can get a nice result for the fit. Here is the case when I basically used a kind of cross-validation, and I found a value of here of being 2 to work well, and you can see that does a decent job when I have gamma equal to 10. Not wonderful, because you do see these little wiggles and oscillations, but that was sort of the best I could do using this relatively high capacity value of gamma for the radial basis function. You could also go through and do cross-validation, not only to tune the variable lambda, but also at the same time tune the variable gamma, which would control kind of the length scale over which I'm kind of interpolating, at least for finite data. Now, of course, as a number of data points becomes much larger, this fit would potentially improve quite significantly. Any questions about the radial basis function fit? So let me show you what happens now if I make this choice for lambda. Here I'm going to choose 0.1. And now we're going to do a sweep over the range of gamma. That's basically the other hyperparameter, which was the width of the radial basis function. And that tends to be the case when you're using kernel ridge regression, is there's going to be certain hyperparameters that come intrinsically from the objective function, in this case, the ridge regression, that lambda parameter, versus hyperparameters that come from the specific choice of kernel. So in some sense, you're trying out a whole range of different kernels in some sense. In this case, I'm staying within the class of radial basis function, but there's no reason why you couldn't try polynomial kernels or Fourier kernels and so on if you wanted to do a wider sweep over possible models. Okay, so this is the same kind of questions I had before. Cross-validation can be ultimately used to try to select these well. And so you can kind of just get a feel, again, what happens as I take the kernel from being very wide, obviously doesn't fit the data very well. And then if I look at the case when I optimize with the kernel being very small, in other words, the RBF being very small, you can see then you end up with, again, that overfitting. And then that could be compensated again by a choice of lambda. Here I just fixed lambda and just wanted to show you what happens as I sweep over kind of the widths that I've chosen for the radial basis functions. So you can see there's kind of a sweet spot in between there. And again, if I go through and I do kind of a careful study, you find that that's probably one of the better choices for gamma, given that choice of 0.1 for lambda. And again, cross-validation is the way you would actually do this in practice. Okay, so that's showing that we can use linear regression methods to fit pretty well even nonlinear functions by use of kernelization. And again, I'll just pause there if there are any questions about this.
Does the gamma parameter in the kernel end up choosing that to correspond to some kind of length scale in the data that you observe?
In theory, you can choose gamma however you like. Yeah, if you knew something about the problem that you're working on, like maybe the variations don't go below a certain length scale, then you probably choose gamma larger than that length scale so that everything else is noise and you wouldn't overfit it, so kind of filter. If you didn't have a lot of prior knowledge about the data set, then you could do it through cross validation. And I'll talk about it in one of the lectures. But basically the idea is what you do is you leave out a certain subset of the data and you do the fit. And then you do another randomized sampling of your data where you've left some out, do the fit again. And if you see things wildly changing, in other words, if you see large variance, that's probably an indicator that you didn't choose a very good value for gamma. So what you try to do is you try to make sure the fit is obviously giving you a low value for the loss function, but that the variability is also simultaneously small. And it's related to that whole bias variance trade-off that we were talking about in some of the previous lectures. So that would be one way you could try to choose the gamma. Yeah. So it's a really important issue, though, how you choose these hyperparameters in practice. And as you can imagine, as you get more hyperparameters, the more challenging it becomes. In fact, here you could also do something which would be just make a grid of all the different combinations of lambda on one axis, gamma on another axis, and do this cross-validation that I mentioned. See which one gave you simultaneously a low residual and small variability, and that would be kind of the sweet spot for the lambda gamma choice that you would make. That's one way you can do the regression. That's kernel ridge regression, very useful technique and really the foundations for a lot of different regression tasks, even when using things like neural networks that can often be an insightful way to go, giving you some insights into possible choices of architectures as well as training protocols. Okay, support vector regression is another technique that I want to show you because I think it's also really interesting and useful in a lot of different contexts. And the idea of support vector machine, just like support vector regression, rather, just like support vector machines, is what we're going to try to do is we're going to try to pick a regression method that creates kind of a margin over the data where we're not too sensitive to the features of the data over that margin. And then outside, we try to keep ourselves kind of fitting between the data. I'll make this a little more clear in a minute, but the idea is suppose I had something like a linear regression task, but the linear data looks something like this, and then there kind of was a bunch of outliers as well. Well, there's going to be many lines that kind of go through that data. Comparably, if you were to just simply use a kind of naive least squares fit. And so this is often useful when the thing you're trying to fit is kind of fuzzy in some way, and you have a lot of outliers. So the idea is, obviously that green line would be probably the target line that you're after, but there are many others that kind of fit within that region involving the red points. And so just like SVMs, we're going to try to kind of, use some type of marginal idea to come up with a good geometry for the final model. So imagine, you can find some kind of margin that kind of covers the red points well and, excludes these outliers in red, lighter red that I'm showing here, pink. Okay, so the idea is that we're going to use a slightly different loss function than when we were doing the least squares regression. And in particular, we're going to use a loss function that kind of has this epsilon insensitivity built into it, so that as soon as we only really count the errors once they get larger than epsilon. So the idea is that if I'm looking at a point and I'm within epsilon of that point, we're going to say, okay, you did a good job in fitting that point. But once I, am farther than epsilon than the target point, then we'll start counting penalties. Now, again, there's many, functions that will satisfy minimizing this. So we're going to have to also think about how to regularize that. And as you can imagine, just like in the support vector machine case, we can go through, we can do a generalization analysis of, which models have better generalization performance, and then formulate an objective function based on those insights. And so just like the previous theorem that I showed you, the hypothesis space will be the same as before. We'll have the same technical assumptions. The only difference is going to be in the loss function. And so if you go through and you derive the generalization bounds in that setting, which again just boils down to a bound on the Rademacher complexity, it's all back to that same general bound that we showed a few lectures ago, then you'll get this for your right-hand side. And so under the this epsilon insensitive loss function. Okay, so then what's nice about this is you can see the bound takes the abstract form of being an empirical risk for that bound, plus a term which scales like capital lambda. And so this is the main thing you have control over, is capital lambda, right? Because that came in here. So what this suggests, if we want to minimize the right-hand side, is we balance how small we can make capital lambda versus how small we can make the empirical risk. Okay, and then if we can make this small, then that gives us a good handle on getting good generalization performance. So in other words, if there are two models that do equally well under the empirical risk, we should pick the one that has the smaller lambda. That's what this amounts to. So it's very similar to the kernel ridge regression idea that we had before. And so the optimization problem then takes on this form where the first term is coming from trying to make capital lambda small, and then the second term is just trying to make the empirical risk small. And then there's one hyperparameter here, which is that trade-off. I just chose to put the lambda in front of the second term. That's the C, and then that's our hyperparameter as before. So you can think about C as being effectively lambda inverse. I put it in this way so that it would look similar to when we did the non-separable support vector machine. You can see it's essentially the same objective, where this is kind of like the slack variables, and on the left here is the usual L2 norm on the weights. So that's hence the name, support vector regression. And if we go through and we were to do a formulation in terms of the dual variables, you would see that it will have some of the same properties support vector machine, where only a certain subset of the data are going to play a role in determining the coefficients of W. And as you can guess, everything inside this little dotted lane, in fact, will not activate the Lagrange multipliers. Okay, so the interpretation of this is as follows. You're only going to incur an error for stuff that lies outside of those dotted lines. And then basically what this is going to cause the fit to do is to try to use the curve to overlap as much of the data as it possibly can. Okay, so this is useful for certain types of regression tasks where you have a situation where the data you're interested in is kind of densely packed but kind of blurred out, and then there's a lot of outliers. This provides a really nice filter for performing the fit. So you kind of fit this tube that covers the sort of dense or dominant part of the data set. So again, very useful for certain types of regression tasks. Okay, so let me show you what happens. This, again, helps filter out high frequency noise, outliers. You can also account for density effects and so on. So it's a really nice technique, and it really does behave qualitatively different than the standard sort of least squares strategy that you're probably most familiar with. Okay, so I thought that was something important to give you some exposure to. Okay, so let me show you how it works in terms of the dual formulation. So we can go and we can reformulate just like we did before in terms of these slack variables. I'm going to introduce two of them. We'll call them xi and xi prime. Basically, the idea here is these xi's are going to say which direction you're kind of deviating from hitting the target. So if you sort of deviate in one direction, we'll call it xi, and we'll require that the difference between this decision, or not decision function, but the actual linear regression function minus y. Basically, if you're less than epsilon plus xi, that'll be the first slack variable. So if you go in that direction of being positive, that'll be xi. And if you go in the direction of being negative, undershooting it, then we'll call it xi prime. And so in that way, we can kind of characterize, how much you're sort of violating being outside these dotted lines here. And that's when the xi's activate. Okay, and then the objective function, if you look at it from that perspective, if you add these two together, you'll see that this actually comes out to be precisely what I had on the previous slide in terms of that epsilon loss function. If you're less than epsilon already, then the slack variables can be 0, and they won't incur any penalty up here. So it's just a reformulation of what I showed in the previous slide. Okay, so now that becomes useful when I start doing the dual formulation, because now my primary variables are w, xi, and xi prime. And then what happens is if you go through and you write down Lagrangian, you compute the gradients in w and xi, xi prime, just like I did for kernel ridge regression. This is the dual function that you'll end up with, that you end up maximizing over alpha, alpha prime. And so then what you end up getting is this optimization function that I'm showing here. And if you look closely, it's very, very similar to what we had before. You can see the role that is being played by the kernel now is, again, conjugated with these alphas. Just now you have these difference of alpha prime alpha. I guess I should have kept C here. C, I believe, is coming in front of the K term. So the hyperparameter C, I just set to 1 for the moment. And then this is on your data, and this is on the characteristics function. All right, so we've done these dual formulations enough times that I'll just leave that as an exercise if you're interested, just go through, compute the KKT conditions, and out comes this when you do the substitution for W. Okay, so this is going to be subject to a few constraints. Yeah, okay, so in fact, yeah, I forgot, when you have the C term in the objective function, that'll come out when we did the non-separable case you saw as a constraint on the Lagrange multiplier. So that's where C comes into the problem now. And these are just arising from the consistency conditions. Okay, so that's just a quick exercise in KKT. All right, so now the representation of the solution, which also comes out of that, is in this form in terms of the Lagrange multipliers. And now, because we did want to do it with a bias, we could always fold that into the feature space. You can actually find the bias as well from all of this, because if you want the bias, then what you can do is use the fact that B has to be this sum here. Again, this all comes from looking at KKT conditions. The complementarity conditions come out in this form, where now what you find is that the Lagrange multipliers are only going to activate if the point xi is outside this dotted region, because that's the only time that the xi's become something non-zero. And so by the consistency conditions, you're going to see that it's really only those things where you're outside that you're going to get contributions to the representation H. So all the stuff inside basically doesn't show up in the representation formula for H. And that's very similar to the nature of support vector machines. We saw that it was only the things that were right on the margin that were showing up in the representation formula for the weight vector W. All the stuff outside, basically farther away, wasn't playing any role. Okay, so hence you can think about these red vectors, these pink vectors that I'm drawing outside as being the support vectors that are supporting the ultimate fit of that hyperplane to the data. So hence the name support vector regression. Okay, so as I said before, when the alpha i's are not zero, then that means you have this equality constraint, which means that the xi's are positive, which means you're outside the epsilon margin. Okay, and then similarly for alpha prime as well, and then for all the xi's inside the tube, you're just going to have alpha I and alpha I prime are zero. Okay, so that's really again a nice little demonstration of how the dual formulation can really give you insights into how the machine learning algorithm is going to behave. How it's, in this case, how it's depending on the data, the final solution that we get. Even though we don't know the final solution, you know, analytically in some sense, this gives us a lot of qualitative insight into how the method behaves. Okay, any questions about that? So I just want to do a much more condensed version for the support vector regression, because I did do everything in a lot of detail for the kernel ridge regression, but it follows the same exact pattern of KKT plus consistency conditions to get this final form. Okay, let me show you how this all works then on a practical example. So I've coded this all up and ran this also on the sine of x fitting problem. And so it's same setup as before. You know, this is still in a class of linear models, but of course we've kernelized them, so we can write it in this form. For now, I've folded the bias in to my notion of what the kernel is. And so we'll just do that. And then now what we're going to do is, again, use radial basis functions, but this time we're going to use the support vector regression framework. So all the things have been kernelized as before. It's just now that instead of using least squares, we're going to be using this epsilon insensitive loss. And so what you're seeing here in the lower right in my figure is the blue region is basically showing you the epsilon insensitivity region. And then what I decided to do is color code the data points as I'm fitting to show you which ones are support vectors and which ones aren't playing you know, a role in terms of the representation formula. So remember the difference we had there with alpha I, alpha prime. So what you can see here is the black and red points are my data points. The green curve is my initial solution when I had an epsilon of 1.5. And you can see that I get this, this green function here. And I believe gamma I chose to be 1. So this will be a little bit smoother than the initial RBF case that I showed before. I had gamma 10 before. And then I found that when you did some tuning, around 1 was very nice for the sine function because it has relatively low frequency oscillations on the scale that I'm showing here. So the blue region now is going to be epsilon insensitive region. So in this case, that green curve is being determined by only 1, 2, 3, 4, 5 points, right? Those are the support vectors that are showing up in the representation formula. I mean, the black points, of course, are playing a role because by overlapping them, I'm essentially incurring zero loss. So if I had chosen other models, you know, they might not overlap as many points. So the combination of the overlap plus those support vectors are determining this green shape. Okay, so it's not a wonderful model, but it's not also that horrific either, considering all the outliers and everything that you see here. All right, so now let me run through the hyperparameter, which is epsilon. So I'm going to choose a smaller and smaller, you know, insensitivity range. In other words, I'm going to allow less and less flexibility in data that I ignore any loss on, meaning that I have to then overlap better and better the more dense regions of this data set. Okay, so that's now the fitting procedure using this support vector regression, and you can really see the benefits of having that ability to kind of deal with outliers a little more effectively than when you do least squares regression. In some sense, the kind of support vector regression kind of has the outliers pushing you towards the high density regions, as opposed to the outliers kind of pulling you like they do in least squares. At least that's the intuition that I like to use. So you can see here now that all of these red points then become support vectors pushing the green curve really to this high density region that I'm showing here, where it tries to overlap as much as it can. And you can see that it's managed to overlap quite a few of them, right, that you're seeing here in black. And now you get a very nice model for the sine curve from this RBF framework. So the same, you know, it's interesting because the underlying representation space here is exactly the same as we had in the kernel ridge regression case. The only thing that's changed here is the choice of loss function. So I think this really illustrates that point that it's really important to think carefully about these different facets of your formulation of the learning task. So again, this is, you know, benefiting a lot from being able to rule out those outliers that you see. Okay, so this is just showing where I stop it for a different value of epsilon. So let's suppose now I fix epsilon is 0.1, and now what I'm going to do is I'm just going to range over different gamma, so you can kind of see how it depends on the capacity of the fitting functions, the kernels that I'm using, where I'll make the blobs, the RBFs, smaller and smaller width, right? That's bigger gamma, of course, given this functional form. Okay, so let's do that for a fixed window there, and you can see that it does pretty well, even for fairly large choices of gamma. And of course, then at some point, it ends up overfitting, as you're seeing here. And again, you could use grid search and cross-validation ultimately to choose those hyperparameters, in this case, which would be epsilon and the gamma. Yeah, and that's just showing that if you choose the value of gamma being 7 times 10 to the negative 1, you get a pretty good fit here. So let me compare these two just side by side, just so you can see the kernel ridge regression working in conjunction or side by side with support vector regression. I guess they're technically two separate optimization problems that I'm solving here. And so this is what you will get. So it's the same setup as before, just using the two different regression techniques, and you can now get a feel for how they behave as I vary the gamma parameter, for example. So here I've chosen epsilon to be, I believe, 0.1 as before, and now I'll vary gamma, and lambda is chosen similarly on the previous slide, whatever that last case was that I did. Yeah, and so you can see that again, you know, without you know, doing any, if you don't do hyperparameter tuning for the width of the RBFs, you can end up with trouble where both methods overfit, and you can see that, you know, they're both behaving comparably bad. And then now this is the case where I've done a little more tuning of where I pick gamma, and you can see that they give pretty comparable results in this particular case. I want to show you another class of regression methods that are also really helpful, often for very high dimensional data sets, in particular arising in inverse problems in imaging and related to PDEs and mechanics. And this is the LASSO regression. And so the idea of the LASSO regression is we're going to replace our L2 penalty function So what I've showing here is the level curves of a linear objective function, just to give you a feel for what the L2 regularizer is doing. And as you remember before, if I try to minimize this linear function over the linear objective subject to the L2 regularization, it'll tend to find the solution that's located, which, where I've illustrated here, which will try to balance these two things. So imagine the linear function is such that if I were to go upward here, I'd go to smaller and smaller values. And then the L2 regularizer, if I go towards the origin, of course, I get smaller and smaller values. Those two things will tend to compete. And where I'll tend to end up is at a point like that. Now, what's really interesting is if you look at a L1 regularizer, so in other words, I just look at the sum of the absolute value of the weights, that will actually get me geometrically a very different kind of regularization in terms of where I end up. So again, the linear model is trying to pull me away here upward to the right. And this L1 regularization, I've drawn the level sets here in blue with these gray lines. And what the L1 is going to do, if you look at what an L1 ball looks like, the L1 ball looks like a diamond. So all the points in, let's say we're in R2, all of the points that have a given L1 norm of 1, let's say, are going to be on this little diamond shape, right? Because if I'm at the point 0, 1, that of course is L1 norm 1. So that of course has L1 norm 1. And if I'm at the point 0, 0, 1 here, that'll have L1 norm 1. And then of course it's going to be a line of weights that have L1 norm. And then you can similarly do it with the signs reversed, and that'll get you this diamond shape. Now, if I look at this, this curve in red here, this is a value of the objective function. If I now look at what point on this red curve has the smallest L1 norm, those points will tend to get pulled towards the coordinate axes. And so this qualitative difference has really profound implications in practice, because what this amounts to, if I look at the weights, if I'm pulled to a coordinate axis, what happens to many of my weight components? So for example, in this one, if I'm in the L2 case, I'll have contributions both from the W1 component and the W2 component. Whereas if I go to the L1 regularization, you see all of a sudden, all of my contributions from W1 disappear. They'll be zeroed out, and I'll only have contributions from W2. And so you can just imagine, doing this in much higher dimensional space. This diamond shape will tend to pull the solution that I have towards a coordinate axis, which has the practical implication of actually sparsifying my weight vector. In other words, it'll tend to zero out many of my weight components, only keeping the sort of bare essential ones that I need in order to get a good value for the objective function. And so the L1 regularizer tends to be a really nice regularization for many problems, especially rising in inverse problems, in particular cases like tomography reconstruction, where we know a priori that the final solution should be sparse in some way. Okay, so this is the LASSO really is going to be very much like kernel regression. The only difference is now instead of using L2 regularization, we're going to use L1 regularization, which will have this inductive bias towards sparsifying the final weights that we end up with. Okay, so again, just like before, we can go through and prove a generalization bound for the case now of linear models where we use an L1 norm now on the weights by this capital L1. And all the other technical assumptions are basically the same as before. And the bound that you get is as follows. It says that the empirical risk will bound the generalization error, the true risk, by something proportional to basically the L1 norm of the weights, plus some terms related to our sampling confidence like we had before. Okay, so capital N here is just the dimensionality of the feature vector, little m is the number of data points, delta is our usual sampling confidence. Okay, so again, if we were to use now quadratic objective functions, you can go through the same logic that I went before. The usual minimizer would be there if I did ordinary least squares. If I do least squares with L2 regularization, I'll tend to get pulled towards the origin to that new solution point. Similarly with L1 regularization, ordinary least squares will tend to be the point that I'm showing in the middle of the gray disk here. And when you then do L1 regularization, that'll tend to actually pull you towards the coordinate axes, as you can see here. So that's where the sparsification again is going to come into play, even for doing things like quadratic, objective functions like regression. So the optimization problem then is going to be to do regression with least squares as we had before, and now to use an L1 regularizer. Okay, and so there's a couple different ways we can formulate the problem. As we mentioned before, you can also turn this penalty term into a hard constraint with an appropriate choice of capital lambda 1. And so therefore, this objective function is basically going to try to minimize the right-hand side of this generalization bound. Okay, so if you can get this to be small, then in terms of this generalization bound, you can get a nice handle on the generalization performance. Now, one of the downsides of using L1 regularization, though, is we no longer have dot products, right? L1 is a very different type of norm, and so we're not able to use the kernel trick there. And so the drawback is that we will have to potentially do computations of those inner products in the feature space that we're working in. But on the other hand, oftentimes that sparsification bias that we get is worth the price for many problems. So anyway, just keep that in the back of your mind that the kernelization techniques won't be as immediately applicable in this case. So as I mentioned before, when you have high dimensional regression problems, that is where the weight vector becomes very large, then this sparsification bias can be really helpful, meaning that having a weight vector that comes back to you where most of the weights are 0 often is going to give you a far superior model than what you would get under L2 regression, where you'll often end up with lots of little weights as opposed to ones that are pulled towards the coordinate axis and zeroed out. So, okay, so this has got connections to compressed sensing and other fields of inverse modeling. Okay, so let me give you a practical example of an application of the LASSO regression. And in particular, in the last few minutes, I just want to talk about the problem of tomography. And so this is a field that's benefited a lot from recent developments in compressed sensing, which is closely related to this L1 regularization idea. So in computed tomography, the sort of key mathematical transform that you use to model what's happening in, for example, a medical imaging measurement is this transformation called the radon transform. And so the idea is if you have an X-ray or some other electromagnetic radiation that you've turned into a beam and that you shoot through a sample, for example, a person's body, because you want to image something related to their internal organs or something related to their skeleton, and you want to get a three-dimensional reconstruction of that, you need to solve the inverse problem related to this radon transform. And so the problem that you need to solve is to reconstruct this density function f of x, y, so that the measurements that you've taken, so in something like this this X-ray machine, what you would have is a beam that comes down. You would have a detector, and what you have in hand is not obviously the three-dimensional information immediately available to you of what the density is at location in R3. What you have available to you is actually an integral of the path that electromagnetic radiation took between the source and the detector. And so just to walk you through what I'm illustrating here on the left is we basically will model the X-ray source and its path to the detector through this line, which has angle alpha, offset s from the origin. And then what we're going to do is we're going to integrate along this variable z, which is just integrating along the line from what I'm illustrating here as a to b. Okay, so the information that you have in hand when you get to the detector is, again, this integral from essentially a to b. And for mathematical simplicity, we'll just make the integral go from negative infinity to infinity. So we're going to have not the density itself at R3, we'll have kind of these cross-sectional averages of the density through different slices. And that's what the radon transform gives us in terms of the slice with angle alpha and offset s from the origin. And then our job is to say, can we reconstruct the density function using this sliced averaged information? Okay, so that's the idea of the inverse problem here, is try to reconstruct f given the radon transform of the density function. Okay, so in general, that's a challenging problem. And as with many of these imaging problems, without any further considerations, it's not actually well posed, right? If you make small perturbations in the radon transform, that could lead to radically different choices for the reconstructed density. So of course, what we're going to do is we're going to regularize this problem in some way, as you can imagine. The other thing to mention is there may be many different Fs, which all give you the same values for the radon transform, but some of those might have lots of little artifacts in them that kind of maybe average out, because if you look at it, if I had a little sinusoidal wave and I integrate along a curve like a line like this, I could easily zero stuff like that out. So what we're going to want to do is we're going to want to do this reconstruction in a way where we kind of minimize the density in some sense, so that the density only appears in a subset of regions. In other words, we're going to want to create this three-dimensional voxelization of the skeleton that in some sense is sparse, right? The dense bone mass is really only localized in certain regions, like the skull, the spinal cord, the ribs, and so on. It's not going to be something that's going to be dense everywhere in the three-dimensional space. So this sparsity inductive bias is really relevant to imaging problems like this. So let's go through and let's use the L1 regularizer as a way of doing this inverse problem. So the optimization problem is going to be to choose from our class of models. In this case, we're going to make the model h of x I, y, I. That's just going to be the hypothesized density at that location in space. I'll do it in 2 dimensions just to make the mathematics a little easier. So this will be the x and y location in space. And so you can think of h of xi, yi as basically just being an image. And then the idea is we're trying to find the pixel values of the image, which are telling us the density of the bone, so that when we apply the radon transform here, we get back what we measured in the experiment. Okay, so the problem we're trying to solve is we're trying to minimize over the space of these 2D density maps. Again, we can express it in terms of pixels. And then we're trying to find the density map that most closely approximates the radon transform information that we have that we would have gotten for a given target function f. And now, as I mentioned before, solving this least squares problem isn't well posed. And so we're going to make this additional regularization that out of all the models that seem to do a pretty good job of fitting the radon transform data, that we're going to pick the one that has the smallest L1 norm. So that's going to tend to sparsify the solutions. And in practice, what that's going to lead to is it's going to lead to results that have less ghost artifacts. So sparse density maps, as I mentioned, are inherent in many problems that come up in scientific imaging, medical imaging, engineering characterization, industrial applications, and so on. Okay, so this L1 regularization idea we'll see come up in some other settings if we end up talking about compressed sensing, for example. So let me show you how this plays out on a practical example that I put together. So what we're going to do is we're going to reconstruct the density map from that projection data, and I'm going to compare using kernel ridge regression, that would be the L2 regularizer, with using the L1 regularizer, just to give you some intuition of how important L1 regularization is and how big a difference it is. So here's the original density map that I'm going to start off with. That's quite sparse, as you can see, right? I just have these little blobs here, and we're doing this all in 2D. So we can use the 2D radon transform that's illustrated up here in the upper right corner. So let me do the kernel ridge regression reconstruction of this. So in other words, I'm going to solve that least squares problem with the radon transform plus an L2 penalty. So I do that, and this is what I get, right? So it's not maybe horrible, but it's got all of these weird little artifacts in it, right? All those little crisscross lines. And so you can imagine if you were trying to medically diagnose something and you got an image like this, you might question, hey, is that thing that I'm seeing really a tumor or a fracture in a bone, or is that an artifact of the reconstruction procedure, right? So that's why it's really important to try to get rid of these artifacts. So it's definitely correlated with the density map, but it's not such a great solution, right? And that's because if you think about what L2 regularization is doing, it's just kind of shrinking you, pulling you directly towards the origin. Whereas the L1 regularization is going to tend to push you to one of the coordinate axes, and that's going to tend to zero out a lot of the components of the weight vector. Here, the weight vector is the image, right? Because W is just a linear combination of all the dyadics to build up that pixelized image. So here you have the L1 penalty, And you can see that you do much, much, much better. And you can see that I put a very small little weight here on the L1 penalty. So even a really modest L1 penalty leads to a massive increase in the performance in terms of how nice the reconstruction is. Now, this still has artifacts, and I'm going to fine tune this in 1 minute, and you'll see I can do even better than this. But you can see that this really primarily emphasizes the regions where I had density in the original sample. So this is doing a pretty good job of reconstruction. This one has all kinds of what we call ghosting artifacts. Okay, so here's now kind of a sweep. My alpha here is the same thing as lambda. Just when I put it together in Python, I happen to use that letter. Okay, and this is just showing sweeping from a small penalty to a fairly large penalty, what you get there. And so you can see that there's kind of a sweet spot on the right before making my lambda parameter or alpha parameter too big and then kind of blacking out the whole image. Of course, that's a very sparse solution, right? If I choose all my weights to be identically 0. Okay, so I realize I'm running out of time here, so let me just show you what the optimal value look like. So I played around with a little bit here. This is for lambda equals 0.01. That does a pretty good job in reconstructing the original sample. If I make it obviously too big, I start to sparsify too much, and it kind of washes out. And of course, if I make it very large, then I completely sparsify to the point where I have no non-zero weights. So with a little bit of work with cross-validation, you can see that you can use this lasso technique quite effectively to learn sparse representations of different solutions to inverse problems. So I think this is a nice illustration of some of the importance, again, of thinking carefully about your machine learning task and really tuning up the type of loss function appropriately for that task.
So I gave a few examples of regression and how it plays out in practice. There are many different forms of regression. Essentially, it's a task of selecting a model H, which allows us to predict outputs Y given inputs X. And so we saw that we could formulate, of course, problems using least squares errors, and that led to the ordinary least squares approach, which is one of the most widely known approaches to regression. But we saw that that has some drawbacks, and that if you just do ordinary least squares, you can be sensitive to noise, and there can be other issues that arise. And so that motivated introducing various forms of regularization. And we saw that you could get better performance for many problems if you introduced a regularizer. And so one natural one to use is the L2 norm of the weights. And if you do that combined with kernelization, that led to our kernel ridge regression method. And so the advantages, of course, of kernelization means that we don't have to do the regression in the native feature space. We could reduce the problem back to kernel evaluations. We saw further that for some problems, especially when there are lots of outliers, there were some benefits of using these support vector ideas, and this led to the support vector regression based on a margin in the loss function. And we saw that that could, again, be helpful for certain learning tasks. We further saw that in tasks where there's some prior knowledge about sparsity of the underlying representation in terms of the weights, this led to an L1 regularizer, and in particular to what was called the LASSO. And so that can be helpful, again, especially when you're working with high dimensional problems and where you have some prior knowledge that the solution model that you're looking for has certain features related to sparsity, for example. And so we saw an example of that in an inverse problem. I should just mention there are many other forms of regression that can be used in practice. Really, the key to getting good performance out of your regression methods is really thinking through the particular learning task and trying to utilize mathematical structure of that specific task to the extent that you can. And so these are just some alternative methods that can be used with that in mind, or can be used to introduce other types of inductive biases. So thanks again for joining today, and look forward to seeing you in the upcoming lectures.